them together. So here are two resonance forms for ozone. And they look the same, but they're actually different because of the different atoms. And in fact, neither one of these exists in real life. The original term resonance comes from the idea that when this was discovered or when it was theorized, the thought was that the molecule would be flipping back and forth. So it would be resonating between one and the other. So like the electrons would sometimes be bound to the one on the left and sometimes be on the one on the right, and they'd be flipping back and forth. But now we know that that's not really the case. And what really happens is that the resonance forms form something that's really hard to draw that we call the resonance hybrid, which is sort of like a combination of both of them. So we might draw it as almost like a dotted line. If you imagine averaging those two together, what they would look like, you know, it's not going to be perfect, but it's something like that. The resonance hybrid is an average of the resonance forms, and that's what we actually see. So what do we mean that we actually see that? It means if you were to take ozone and do some spectroscopy on it, calculate the bond lengths, you'd find that it had two equal bonds that were about right in between a single bond and a double bond. The double bond's shorter than a single bond, and those bonds in ozone would be equal and would be about 1.5 bonds worth. In Lewis, because that's so hard to draw, because in Lewis structures, we don't have anything to express these ideas of half of a bond. Like, that doesn't mean anything in a Lewis structure. So when we get into molecular orbital theory in the next chapter, that'll make a little bit more sense. But what we can say is that the real ozone structure is kind of halfway between those two. And so we would expect those oxygen-oxygen bonds to be halfway between a single and a double bond. But they are actually equivalent. If they were flipping back and forth, you would expect to be able to isolate double bond, single bond, or single bond, double bond, and have it be kind of a lopsided molecule. But it's actually a symmetric molecule. This also applies for when you have this type of resonance that's not equal. So in ozone, these two resonance forms are exactly equal. There's no, like, one's not better than the other, one's not more stable than the other. So the average of the two is an exact, you know, regular old average. In something like this, where the structures are clearly different, we're gonna have to do a weighted average to figure out what's going on here. So let's look at the resonance forms for thiocyanate. We've got a couple of them here. They look nice. None of them are violating the octet rule, but they are missing formal charges. So let's add those in. Does it matter if you draw it angled like this or straight like this? If we're just drawing the Lewis structures, it doesn't. When we get into shapes in the next chapter, then that will change. But for Lewis structures, it doesn't matter how you draw it. So in this resonance form, there's a negative formal charge on the nitrogen. In this one, there's a negative formal charge on the sulfur. I'll draw them up here. And I'm going to make them all straight just so they look the same. Okay, so there's one. And because it's an ion, we often put these brackets, though if you have the formal charges, you don't really need the brackets, but certainly one or the other is always necessary to show that you have an ion. Oops. Did anybody find the third resonance form? There's a third way that we can draw this molecule.
It was like
It still works.
It's like triple bond of sulfur and single bond of nitrogen.
Yeah, it's going to be kind of the opposite of that second one, the triple bond from sulfur to nitrogen, or sulfur to carbon, and then the single bond from carbon to nitrogen. And in this case, there's going to be a 2- formal charge on the nitrogen and a positive formal charge on the sulfur. So they still add up to -1 overall. Anytime you have a greater than a 1 formal charge, either plus or minus, that's a good sign that that's not a great resonance form. So that's going to be. So what this tells us is if we want to get a picture of the overall structure of thiocyanate ion, we would say, all right, here are the 3 resonance forms. Which are going to be the most important? So we would say first, we know those first 2 are going to be the most important, the most contributors to the overall structure. Which is just another way of saying that that last one, we know from the really high formal charges, is not going to be as stable. So when we think about the overall hybrid structure of thiocyanate, we would say, well, we're pretty sure that it's not going to be like, it's not going to look much like a triple bond between sulfur and carbon. It's going to be more like in between a single and a double bond. And we're pretty sure that the carbon-nitrogen bond is going to be between a double and a triple, not like a single. Because that last one on the right, we know is really not a great contributor. So of these 2, which do you think is the most important resonance form? Which one contributes most to the overall structure? The first one or the second one? Because in this case, they're not equal. Ozone, they were equal. This is not equal because either you've got a negative charge on nitrogen or a negative charge on sulfur. Those are 2 different things. So which is better from an energy standpoint? Which is more stable? Do you remember how we evaluate that? Yeah.
Is it the first one?
It is. Why?
If you add an electron to nitrogen, it gets the number.
I think you're getting that mixed up with something else, but you're right that it's the first one. But what is it about nitrogen that makes it better to have that negative charge? Yeah.
The whole thing is symmetrical.
The whole thing is symmetrical. That's a nice idea, but that's not always going to be the case in terms of being the better structure, being more symmetric like that. So that's a possibility. Yeah, go ahead.
Isn't nitrogen more electronegative?
Yeah, that's really the key here that we're looking for, that when you have competing resonance forms like this, the more electronegative element is going to be more stable with the negative charge. So nitrogen is above sulfur, more electronegative than sulfur, so we would expect nitrogen to stabilize that negative charge a little bit better. So our guess is that that one's the best. Now, how do you check something like this? Well, you check it experimentally by bond lengths. So if I look at like standard basic bond lengths, estimated bond lengths in picometers, a sulfur-carbon single bond is 181 picometers. A sulfur-carbon double bond is 161 picometers. A carbon-nitrogen single bond is 147. Carbon-nitrogen double bond is 128. And a carbon-nitrogen triple bond is 115. So those are just like known values that I looked up from this table. In the thiocyanate ion, we see the sulfur carbon length is 167.9 picometers. And the carbon-nitrogen bond length is 118.7. So we can compare these numbers here and look where that fits in. Sulfur carbon's 167.9. That's right between a single and a double, right? Or yeah, single and a double bond. 168 would be like right in here. So that tells us that in this actual structure, these two forms are being averaged, and we're seeing right kind of in between, maybe a little bit more on the double side than the single side, because 168 is a little closer to 161 than 181. On the other one, the carbon-nitrogen 119 is between a double bond and a triple bond. So we're averaging those two together. So in the real structure, we can say that those two would be averaged together. And the other interesting thing, if you look at the experimental data here, is that the one on the left seems to fit with the carbon-sulfur bond length better, but the one on the right, or the middle, seems to fit with the carbon-nitrogen bond length better when we look at it experimentally. So that tells us that these ideas of like which one's the best based on the resonance forms, based on the formal charges, whatever, it's really just kind of a rule of thumb, and it's not always going to work. We're going to need a little bit better theories if we really want to get into the true structures of these things. But this kind of gives us a good start. All right, questions about drawing Lewis structures, resonance forms, any of that kind of stuff? Okay, the last bit of chapter 9 deals with bond energies. So we'll look at that, and then we'll take a little break and go on from there. This looks like something like this. We could take a molecule like chlorine gas, and in a special experimental setup, you can break that bond apart. Even though that's a stable molecule, you can actually break that apart and make two chlorine atoms at high energy that are also in the gas phase. So we're talking, this is not like just something that happens in normal conditions. You need some specialized conditions for that. But you can measure how much energy it takes to do that. If you've got a mole of that, it takes 243 kilojoules of energy to break that up. So we would say then that, where is it? So we would say that the chlorine-chlorine bond has an energy of 243 kilojoules per mole. So every mole of chlorine-chlorine bonds takes 243 kilojoules of energy to break it apart. And similarly, if you do the reverse reaction, you're going to release that much energy. So you're going to release 243 kilojoules per mole of energy. And these aren't numbers that you need to know, but you can look in the book and find, or in textbooks, handbooks, energies, or internet stuff, whatever. And you can find a table that looks like this. We'll put it in the notes just so we can refer to it later. A table of bond energies. It gives you some of these numbers. Okay, so what's the energy of these bonds? Now that energy is directly correlated to the strength of the bond. So we would say that a bond with a higher bond energy is a stronger bond. There's more energy contained within it. So what are some of the really strong ones? What are some things that we can learn from this table? Things like a hydrogen-hydrogen bond. That's probably the strongest single bond on the table. I'm looking quickly to see if I'm wrong, but I'm pretty sure I'm right there. So that's why we talk about things like hydrogen fuel being really, really, really energy dense, because there's a lot of energy in a hydrogen-hydrogen bond. Carbon-hydrogen bond, carbon-carbon bonds, those are all really high energy bonds. That's why things like fossil fuels are so hard to get away from, are so hard to replace, because there's so much energy in relatively small amount of mass with these bonds, and the other types of materials just don't have as dense of energy, just don't have as much energy, chemical energy in their bonds. What other kinds of things can we find from this table? Well, we can look at some similar stuff, like if we look at carbon-carbon, single bond, double bond, and triple bond, what do you see there?
I just wanted to say hydrogen fluorides.
Oh, you're right. Yeah. Okay. HF. I forgot about that one. So that's going to be a stronger bond. Thank you. So what do we see about these three? What kind of trend? What?
More bonds, the bond energy to bring them gets stronger.
Yeah, the bond energy is increasing as we have multiple bonds, which makes sense because you've got more electrons being shared, so it's going to take more energy to tear those things apart. You can also look at some trends, like if we look down the halogens, the hydrogen with the halogens, we've got HF, HCl, HBr, HI. So we have a decreasing bond energy as we go down the periodic table. We can see if that trend holds in other situations. It kind of does, kind of doesn't. Like if we look at the nitrogen versions of that, kind of jumps around a little bit. If we look at carbon, where are the carbon ones?
Carbon was, back where you look at bottom left.
So CCl, but I don't see CF and CBr. Yeah, so we'll have to look at different tables for that. But anyway, so you can say some things about the energies of the bonds. All right. So that's good because if we want to know what bonds are stronger, if we want to know if a reaction is going to happen, we can use some of those things to estimate that. One thing we can do with this, I'll just, rather than redrawing this, I'll just copy it from the book here. We can use something called, here it is. This is something we kind of skipped in chapter 6 because it's not really worth spending a lot of time on. But you can estimate how much energy change there's going to be in a reaction just by thinking about what bonds are formed and what bonds are broken. So in this particular reaction, what we've got here is enthalpy is on the y-axis, that's energy. And we're showing here this reaction. Methane CH4 and chlorine gas are reacting to form chloromethane and HCl. Okay. So that's a reaction that's happening here. And we want to know, first of all, is this reaction exothermic or endothermic? And by how much? So one way we could do that, of course, is to do the actual reaction, measure the temperature change, and do some of these calculations that we skipped in chapter 6. But you can also at least estimate it from bond energies. Because when this reaction happens, you can think about what has to be broken and what has to be formed. So in this reaction, we could think about this as breaking a CH bond and a CL-Cl bond. So we can think about this as breaking off one of the H's from CH4 and breaking off the Cl's to make, or the Cl2 to make Cl and Cl. And then we can think about recombining those. So making a CCl bond and making an HCl bond. So what bonds are formed, what bonds are broken. We can subtract those bond energies from each other and get an estimate of the overall energy of the reaction. All right, so let's look at how we do that calculation-wise. So we say, okay, we're going to break a CH and a Cl-Cl bond. So we look up those two. So we're breaking a CH bond, which is 414. And we're breaking a Cl-Cl bond, which we just talked about, 243. And then what bonds are we going to form or make? We're going to make a CCl bond by connecting the Cl to the carbon. And we're going to make an HCl bond. So we can look those up. CCl is 339. And HCl, that's another high one, 431. Add those up. Seven and 770. And subtract. So the ones that we're breaking are going to be positive because that takes energy. You have to put in energy to break a bond. But the ones that we're making, the enthalpies should be negative because when you form a bond, you release energy. So these are going to be negative. And you put those together and you find that the overall enthalpy of this reaction is going to be what, about 113? All right, so negative 113 kilojoules per mole. So since the total delta H for the reaction is negative, that tells us it's exothermic. Tells us how much energy is going to be released. Now there's other factors here, so when you actually do the reaction, it's going to be hard to measure and actually recover all of that energy, but theoretically, that should be a good estimate for what this reaction produces. And yeah, go ahead.
Does H stand for enthalpy?
Yes. So that's going to be a good estimate for the overall energy difference in this reaction. And you could do this for any reaction, even if you're breaking tons and tons of bonds. You could do this. So let's look at a basic combustion reaction. I'm going to leave the table up here so we can use it, and I'm going to put the reaction on the board so you can try it out. So we're going to look at combustion of methane, CH4 plus O2. You have CO2 and H2O. And then we've got to balance that. Okay. So there's our reaction. Now, in order to do this to that reaction, we need to know a few things. We need to know the balanced equation, which we've got here. And we need to know how many of each type of bond is broken. So for instance, of these CH bonds, how many stay intact in the products? None. So that means that the bonds that are going to be broken here are 4 CH single bonds. What about the oxygen bonds? How many of those are intact? Yeah, also none. But you have to know some things to figure that out. You have to know how to draw a Lewis structure of O2 and how to draw a Lewis structure of CO2 because that looks like O2 and O2. Maybe those stay together. So you have to know that CO2 is actually not, the O double bond is not stayed together. It's actually broken apart and made a new type of bond. So think about the bonds in this reaction. Use the table up there and see if you can calculate the enthalpy change for that particular reaction.
Also,
you can work together.
There's like an asterisk for the CO2 thing. You know, something, right?
Oh yeah, that's right. So the CO2, the O2 and CO, or the CO double bond and CO2 is a little bit different energy than the standard carbon-oxygen double bond. So note that at the very bottom of the table. You see that? So use 799 for each of those. instead of 736. All right, so do just what we did with that carbon and chlorine example to this reaction, work together and see what you can find, and then we'll look at it and see. Yeah. No, you need to do 2 oxygen-oxygen double bonds for O2.
Yeah, that's right. Yeah, right. So what's the one? What's the structure? There is no OH. You can take the OH bond string, which is 464. There's 4 of those.
All right, can I move this table? Okay, so here. All right, so let's think about the bonds broken and formed. In this reaction, nothing stays intact. So every bond on the left is broken, and every bond on the right is formed new. So that means that we've got four CH bonds broken and 2 OO double bonds broken. On the right, we've formed 2 CO double bonds and 4 OH bonds from water. Because we made 2 water molecules, so we formed 4 total OH bonds. So now we got to look up those numbers. I've got them here, so I can write them down. CH bonds are each 414. OO double bonds are 498. CO is special in CO2. So that's 799. And OH is 464. Oh yeah, that's higher than an HH bond too. So what I said before was, oh yeah. All right, so I've got 1656996. So I have to put in about 2,600 kilojoules per mole to break all the bonds in this molecule. And then we get out okay, so delta H for the whole reaction. Products are negative. So it's going to be -2652, -802. Well, I guess it's not really per mole, but minus 802 kilojoules per mole of methane combusted. So you do this reaction, you get that much energy out, which is why, again, fossil fuels like natural gas, which is mostly methane, make for such good fuels because you're getting a lot of energy out per mole. You're breaking really high energy bonds, and then the bonds that you're forming are, oh, I'm sorry, you're forming really high energy bonds. So questions about how to do that? Just multiply the different bonds, subtract. There's some practice in the homework on this. Yeah.
So we're gonna be given these like constants, right?
Right, these numbers, yeah. Yeah. Okay, let's stop there. That's the end of chapter 9. So we'll take a break, come back, and start talking about molecular shapes.
That's the pi bond around, right?
Yes. Although I don't think we're going to get to hybridization today. Maybe.
I guess I'm not working with whatever.
Yeah, we'll see if we get there today.
I have no clue what else checkers is, because that is a pretty big checker.
All right. So the last thing we're going to do today is talk about molecular shapes. We've drawn all these Lewis structures in these various ways, and we don't have a good way of saying, well, is this actually bent or is it straight? Are these things, we would call that like a T-shaped or planar, or is it bent in some way? We haven't talked about how to evaluate that. So that's what this part is all about. First, we're just going to look at the different shapes and how this is determined and what the theory is behind it. Then we'll look at some of them. And then on Thursday, we'll get into the later part of the chapter, which is, I think, a little bit more interesting, where we get away from some of these more simplistic models and start talking about what's really going on. All right, so the major model that we use for this, or the major theory we use this, is VSEPR, which we pronounce Vesper, even though it should be like Vesper. I don't know. We call it Vesper. And it stands for valence shell electron pair repulsion. And it's actually a very simple theory, even though it's surprisingly predictive and it works very well. The idea here is just that electrons repel each other. That electron pairs are going to repel each other and want to be as far away from each other as possible. And where are the electron pairs in molecules? They're in bonds and in lone pairs. So the electron pairs that we're talking about here are both the bonds and the non-bonding electrons. So we would take a molecule like thiocyanate over here. And if we're using that theory to evaluate these two models, either the bent one or the straight one, which one represents the electrons being as far away from each other as possible? The straight one. So does everybody see that? Here, if we imagine these bonds between the carbon and the other elements as being these electron pairs that are repelling each other, if they're at 90 degrees, like in this picture, they're much closer to each other than if they were at 180 degrees, like this. So we would say that this is the more predicted shape, because that way the electron pairs can be as far away from each other as possible. You see how that works? That's the whole thing. That's the whole theory. Electron pairs want to be as far away from each other as possible. So all that's left is to talk about the consequences of that. What are those shapes that result from the electrons pushing each other away in these different ways? So we define electron groups as either a bond or a pair of electrons. Those are both be considered electron groups. So any molecule that has two electron groups on the center atom is going to take that same shape. Whether it's an ion, like thiocyanate, or one of these weird exception ones like beryllium dichloride, which doesn't have a full octet on the central atom. In each case, we can identify two groups around the central atom. Even though there's double bonds, we call that 2 electron groups. Okay, we would call these 2 electron groups. And so in both of those situations, they want to be as far away from each other as possible. And the structure that results is called a linear geometry, or a linear structure. Makes sense, it's a line. The other way that we identify these shapes is by bond angle. The bond angle is what results from 3 atoms connected together. So if we have something like three atoms like that, this would be our bond angle right here. And for a linear structure, what is the bond angle? What is that angle if you have a linear structure? Yeah, 180 degrees. So for a certain number of electron groups, there's always going to be a geometry, a shape, and a bond angle that you can identify this by. So if you have 2 groups, we call that linear, and the bond angle will always be 180 degrees. Let's move on to the next one. If we have 3 electron groups, for instance, BF3. Now, if we're just drawing the Lewis structure, we might draw this like this. Boron, again, is one of our exceptions, so it only gets 6 total electrons. We might draw the Lewis structure like that. Is that as far apart from each other as those fluorines can be, as those electron groups can be? It's not. How could they be farther apart from each other?
You could bend the top 2 like that. Like
Yeah, they're going to be equidistant. So the way I've got it drawn here, we've got 180 degree here, and then 290 degrees here. That's not ideal. 180 degrees. Because those 90 degrees are going to be, closer. So we can get a better overall repulsion here if we space those fluorines out evenly from each other. If we space those out evenly, the angle that results is 120 degrees. And the shape, we call this shape Trigonal Planar. So we'll have a kind of like a triangle that's in a plane. So it's a flat molecule. And if all those spread out as much as possible, you end up with 120 degree bond angles. Whoa. Another common place we see this type of an angle, or this type of a geometry, is in double bonds with carbon. So if you have this type of molecule, same thing. We can see those as 3 groups. Remember, multiple bonds still count as just 1 group. So you've got the 1 group on the top there, and then the other 2 going to hydrogen. That's 3 groups. So if they totally spread out, that's 120 degrees. So that's 3 electron groups. All right. So now is the first time we kind of spread out into 3 dimensions when we go to 4 electron groups. If we looked at something like methane Ch4, we might draw that Lewis structure as this. And if we were, in fact, looking in just 2 dimensions, like it had to be flat, that would be the best way for 4 things to spread out. But molecules are molecules, they exist in space, and so they can spread out into 3 dimensions. So we can actually get those hydrogens further apart than what we've drawn there. And to show you that, I'm going to pull up a modeling program here. And we're going to draw a whoops, whoa, what's going on? We're going to draw a methane molecule. And see what this looks like in 3 dimensions. So you can kind of get a sense of that. So you've got the carbon atom in the middle, the hydrogen atom on the outside. And so now we see that as a little bit different, right? It's not in just 2 dimensions. It's spread out over 3. And if we stop this so we can look at those angles. So this bond angle now, does that look like more spread out or let's see, how am I saying it? Does that look like a larger or a smaller angle than 90 degrees?
Larger.
It's larger. You see that? How instead of being square, it's larger. So that tells us that those electron groups, those 4 groups, are a little bit more spaced out when they take on this structure. Does anybody know what this type of a structure is called? Yeah, that's a tetrahedral structure. So this is tetrahedral. That comes from the shape, the tetrahedron, which is a regular solid with 4 equal sides, 4 equal angles. And if you imagine the hydrogens being at the corners of that shape, and then the carbon being at the middle, that would be a tetrahedron. So that shape is called tetrahedral. I copy this to the notes. So this shape is called tetrahedral. And these bond angles are about 110. So greater than 90. Oh, you can't really see that, sorry. About 110 degrees. I think in the book, yeah, in the book they always talk about it as being 109.5, which I don't know why for tetrahedral we have to use extra significant figures compared to the other angles, but it's about 110. The other reason for that is, yes, in a perfect methane molecule, it's 109.5, but in pretty much any other molecule, it's a little bit different from that. So it's better to just think about it as about 110. There's no need for that extra precision. So that's our tetrahedral molecule. Now, how do we draw that shape on paper? Well, one way we can do it is just say that it's tetrahedral, or just kind of do our best approximation of a tetrahedral molecule. But as we go on, especially if you go on to organic chemistry, it's going to become important to really express this in 3 dimensions. So the way that we do that, if we use this same molecule here, is we'll draw our carbon in the middle. And then you can recognize that in this structure, if you line up so that 2 of your atoms are directly in the plane of the paper that you're writing on, the other 2 are actually also lined up. One's coming out at you and one's going back. You see that? So these 3 are all in the same plane, and then this one's coming out at you, and that one's going back behind. So we use a notation to do that, where our regular line bonds like this indicate the hydrogens that are in the plane of the paper. And then the one that's coming out at you, we use a wedge-shaped bond that looks like this.
Are we going to be doing this?
Yeah. Why is it? Do you not like it?
It's weird.
What?
It's a little weird.
Okay. And then the one going behind, we use a dashed line like this. So that shows that 3-dimensional geometry. And even though we draw them a little bit apart, the dash and the wedge are actually right on top of each other. So what we're really expressing is this, but of course if we tried to draw something directly on top of each other, we couldn't see it. So we draw it a little bit offset, but understanding that they're actually right in the right spot, right in the same spot. One coming forward and one coming away. So we call this dash wedge notation, or the dash wedge structure. All right.
No, it's okay. We're just shutting down and having some lunch.
So the other important thing here is now what happens when we have electron groups that are not atoms. So rather than going on to the next shapes here, let's talk about what happens when we have electron groups that are not atoms. So instead of CH4, let's look at the structure of NH3, ammonia. The structure of ammonia, if we just look at a normal Lewis structure, looks like this. And so we might say initially, oh, okay, well that looks like 3 electron groups, so it's probably trigonal planar. The hydrogen's all spread out, it's trigonal planar. That's not quite right. And the reason it's not quite right is because that lone pair of electrons also counts as an electron group. So ammonia fits into this 4-group geometry, which means it's going to have a tetrahedral type structure. So it won't be spread out in trigonal planar, it'll look more like this. So the geometry is based on the number of electron groups. We would expect those HNH bonds to be around 110, and they are. And that puts it in the tetrahedral group. But if we actually looked at a molecule of ammonia, we wouldn't see the electrons, because that electron group is on the atom. So what you would actually see is something more like this. So even though this is based on the tetrahedral geometry, because the actual shape that we see is a little bit different, we call the shape, we have another name for the shape, Trigonal Pyramidal. So it's based on the electron geometry, the tetrahedral electron geometry, but the shape has its own name because that's what we actually see. That's the molecule's shape that we actually see. So the books, I just want to make sure I'm using the right terminology from the book. So in this case, we're going to use 2 different terms. We're going to talk about the electron geometry, which in this case would be tetrahedral. So that's including all electron groups. And the molecular geometry or shape does not include the electrons, and so we would call that trigonal pyramidal, kind of like a pyramid shape. And then if we have something like water, we can change that again. So water, of course, has this kind of a structure. How many electron groups there? Yeah, this is once again 4 electron groups. So the electron geometry is tetrahedral. But if you think about what we're actually seeing, we don't see those electrons. So the actual shape, though it maintains approximately those same bond angles, is just called bent. Because that's the shape that we actually see. So I haven't drawn in the bond angles on these two molecules. We would expect them to be around 110, and they are, but they're a little bit different. So let's talk about why. So the bond angle here is about 107 degrees, which again is close to 110. And the bond angle in water is 104.5 degrees. So what's going on there? Why isn't the bond angle 110 if the electron groups tell us that it's tetrahedral geometry? Why is this? Any ideas?
Maybe the electrons are interfering with it or something.
Yeah, the lone electron pairs are interfering a little bit, and that interference is that they require a little bit more room. So they're going to repel a little bit more strongly than the bonds themselves. Let's sum that up a little bit here. So that lone pair or non-bonding electrons, we can say they take up a bit more room. So the bond angle decreases as they kind of push those other elements of those other atoms away. All right, so we go from 110 in methane to 107 ammonia to 104 for water. And we can expect that to happen in various situations. We'll talk about where it doesn't happen also when we get to that. All right. So now we've talked about 2 electron groups, 3 electron groups, 4 electron groups. We're going to look at 2 more because that takes care of most of the common situations that we're going to see. These next 2 can only happen with expanded octet molecules. So when we have 5 electron groups, that's 10 electrons. So we can't have that with any of the second row elements. All right, so now we're talking about things like PCl5. Again, we could draw this like this, kind of like a star shape in a Lewis structure. But that's not really the best situation in terms of all of those electrons repelling each other, because if we use our third dimension, we can get a lot better repulsion there. So let's do that. In 3 dimensions, we're going to have a shape that looks like this. And if we can't see that well, we can also use our dash wedge notation here to show that these are in 3 dimensions. This is going to be our first and only structure in this list that has 2 different bond angles. These are in the same plane, so the angle between those 2 CLs is 90 degrees. But the angles between the ones that are going around the middle are actually more like in a triangle. And so that angle is 120 degrees.
Aren't you measuring it compared to the closer ones?
Which closer ones?
Like that CL you measure, why are you measuring to the CL that's closer than that other one?
The closer ones are 90 degrees away.
Okay, so,
So like this one to this one is 90.
yeah,
This one to this one is 120.
well, like, what about, like, say, the top one to the one to the left of it?
This one,
Yeah,
that's going to be 90.
oh, it is?
Yeah.
Okay.
So in each case here, and so let's take a look. If we can get this in the structure. This thing. Let's see. I don't know if we can get this thing to actually.
There's a picture of it in the book.
There, yeah. It's more fun if we can spin it around though, isn't it? Yeah, that's not minimizing energy properly. Let's see. Oh.
Jason.
It's a good dance. It's trying to find the right spot. So what it's doing is it's computing the energy of all these different configurations and trying to find one that's below the tolerance that I set. But I might have set it so low that it actually can't find it. And it's just going to keep going. We'll see. It's kind of fun though.
Yeah.
Okay, let's stop that. Let's try that again. Whoa. Yeah,
That's not right.
no, that's not right. There we go. Okay. So that's the shape there. So what you've got here is actually atoms that are in two different situations. There are these that almost look linear from here to here. Those are called the axial atoms, meaning they're on the axis. And then you have these three around the middle called the equatorial, like around the equator ones. And so if we look down at it this way, get it a little bigger here. You see a nice trigonal plane there, 120 degrees. But each of those is going to be 90 degrees away from both of the axial substituents
Oh,
there.
okay, yeah, I see.
So you see that shape now?
Yeah, I see now.
All right, so the name for that is Trigonal Bipyramidal. So you can think of it as like two triangle pyramids, like stacked on top of each other, one up and one down. That's where that name comes from, Trigonal Bipyramidal. And so we have these axial and equatorial substituents. So what happens then if we have a structure like this, which has 5 electron groups, 1, 2, 3, 4, 5. And 1 is the electron, is the lone pair. We have a choice to make here. In our other examples previously, we could put that lone pair on any position. It doesn't, like on ammonia, all 4 positions of a tetrahedron are the same. So it doesn't matter where you put that lone pair. But now it does matter. Should the lone pair go on one of the axial positions or one of the equatorial positions? So what idea are we going to use to make that decision? Like what kind of a situation does that does that lone pair of electrons want to be in? The what? Yeah, it wants to be as far away from everything else as possible. So is it farther away from stuff on an equatorial position or on an axial position? Axial?
Equatorial.
Equatorial? Well, I guess that's all two choices. So let's take a look at it. Let's draw it in both ways and try to figure it out. So if we put it in the axial position, it's like, let's just do it like this so we have the same structure. If we put it in the axial position, it's like that. If we put it in the equatorial position, it's going to look like this. So in which position does it is it further away from more atoms? Well, on the left, that electron is 90 degrees away from 3 different other electron groups. See that? Those are the closest ones. And the other one, it's 90 degrees away from 2 electron groups and 120 degrees away from 2 electron groups. And so as it turns out, once an electron pair is about 120 degrees away, it no longer feels any kind of repulsion at all. So this is better. So another way of saying that is that lone pair only really feels repulsion from those 2 90-degree bonds, whereas the one on the left feels repulsion from 3 90-degree bonds. So this is the shape that it will actually adopt. And that molecular geometry is called seesaw. So it kind of looks like a sideways seesaw. All right. So then what happens if we get another one and get another lone pair in there? Like bromine trifluoride. We do this lone pair, we get, or this Lewis structure. We have still 5 electron groups on that central atom, 2 lone pairs and 3 atoms. And so those electron pairs will actually also go on those equatorial positions. And that leaves all those fluorines in a plane. And so that one actually adopts the same structure as the Lewis structure that we just drew. And that's called T-shaped. And then you can go one more step on that. If we have 3 lone pairs, the third lone pair also goes to the equatorial position. So now we have 3 lone pairs on equatorial positions, atoms on the axial position, and that makes another linear molecule.
There's only for 6 electron groups.
There is. So for 6, I'm going to give you the basic structure. And then I want you to work out what happens when there are some lone pairs on there. So for 6 electron groups, let's see, what's a good example of this? We want them all spread out again. Let's see if we can. See if these things can go again. I could just. Whoa. So when we have 6 and they all spread out, we get this kind of a structure. It looks kind of like that trigonal bipyramidal. It looks like you've got 2 on the axis here and then 4 around the middle instead of 3. But those are actually all equivalent. So if I kind of tip this over like this, you can see that those axial ones are also in the same environment. So in this case, all bond angles all throughout the molecule are 90 degrees. So there is no difference between the axial or the equatorial positions. They're all equivalent. And this is known as octahedral. Even though there are 6, which oct usually means 8. So anybody know where that comes from? Yeah, well, close. It's 8 sides. So octahedron is this kind of a shape. Oops. Sorry, not good at drawing these things in 3 dimensions. It's this kind of a shape. Kind of like a diamond shape in 3 dimensions. And so that's got 8 faces. So that's where that term octahedral comes from. But if you,
like what it would look like if you were to somehow like tilt the entire molecule or turns the octahedron or whatever, like you put the molecule inside it.
Sure, yeah. Right. So you have to put that molecule inside it. And you get something like that. That's known as octahedral. And all bond angles are 90 degrees around the whole molecule. So they're all equivalent. All right, so I want to give you 2 different structures to look at that are within the 6 electron group category, but I want you to figure out what the actual shapes would look like with the lone pairs in them. So one is one that we put right up here, XeOF4, and then we'll stick with that same central atom and do XeF4. And see if you can come up with geometries for each of those. You'll need to look at the Lewis structure. One's already down on the board. You can do the other one. Draw the Lewis structure, figure out the electron groups, and then decide or talk to people around you where you're going to put those electron groups so that they're as far away from each other as possible. And that's going to give you your shape. So you can draw them in that octahedral shape, what it would look like if you replace a position with a lone pair. And then we'll talk about the names for those. All right, looks like some good ideas on those. So what we're going to do is put those lone pairs in various positions. Now for the first one where there's just one lone pair, it doesn't matter where you put it because again, all positions are equivalent. So you can just draw that structure. Again, doesn't matter where you put everything. So if you put that lone pair underneath, you end up with this kind of a structure, or again, it could be on the top, could be on the side, doesn't matter where you put it. No matter where you put it, you're going to end up with this structure, which kind of looks like the top half of that octahedron, if you connect those together. And so that's called square pyramidal. And then with the second lone pair, you're going to want to do it opposite the first lone pair, because that's going to keep those two lone pairs as far away from each other as possible. So the second one is going to end up opposite where that first one went, which means we're left with a geometry like that. Those all four are now in the same plane. That's called square planar, and that's the right, because that kind of makes a square. Again, those aren't bonded. That's just the in that way. That's just the shape that I'm drawing. Those are all in a square. So that's almost like how you would really draw this thing on paper. You could imagine looking down on it. Whoops, not FE, just F. Yeah, you can imagine looking down on it like this. And so there's your square planar, that everything is flat and in a plane with 90-degree bond angles. So this is all summed up in a nice handy table on page 436 in your books. Let's grab that. So for each category, you've got the number of electron groups. Whoa, can't see that. The number, let's try that again. The number of electron groups, then the number of actually bonding groups, which is the atoms, the number of lone pairs, what the electron geometry is called, which is always the same within a category based on the electron groups, and then what the actual molecular geometry is called, which is based on just the bonding groups, just the atoms and not the lone pairs. And then it gives you an example of each one and sort of a 3D picture of what that would look like. So we've looked at all those. The nice thing about this is they always go together. So like electron geometry, shape, bond angle, once you kind of put them together, they're always the same. It doesn't matter what kinds of atoms you use. If you've got 3 bonding groups, that's always going to be a trigonal planar, 120-degree geometry. The only other thing you have to know is the names for the shapes, bent or planar. So to practice this, do you have the molecular geometry lab from yesterday? You got that packet? Go ahead and take it out. I'll pull it up here and we'll look at it a bit together. So that's this one here. Yeah, the last several. So for each of these, there's a nice chart here where you're going to draw the Lewis structures and count the number of bonded atoms, the number of lone pairs, the geometry, and the bond angles. Okay. Remember, this is molecular geometry, not electron geometry. We're going to skip, or we're going to hold off on the last half of this table because this has to do with the orbitals. We'll get into that on Thursday. But just the first 4 columns here, you should be able to fill in for each of these. So if you don't have this with you, that's fine. You can just take a look at it up here. So draw Lewis structures, determine the geometry and the bond angles for each of these. Notice here, bond angles, it also says less than, greater than, or ideal, which means you want to look at whether or not there are lone electron pairs pushing on the atoms the way that we saw with water and ammonia. Do you expect that to happen? And if so, that's going to be smaller than normal bond angles. Or are they ideal, meaning everything is just spaced out exactly at the angles that you would expect for that type of group. So let's do one together, and then you can work on the rest of them. Which one do you want to do together?
Let's do A.
A. All right. So first, we're going to come up with a Lewis structure for BeH2. And this is good review for the Chapter 9 stuff for the quiz tomorrow. So we'd say beryllium has 2 electrons. Each hydrogen has 1. So that's 4 total valence electrons. We connect this thing together. That's 4 electrons, so that's it. No more electrons left. Beryllium doesn't have an octet, but that's okay because beryllium is an exception where it doesn't get an octet. All right, so now we want to fill in those different categories. So the first one said, I don't remember, bonded atoms. How many bonded atoms on the central atom? So just 2. Remember, of course, there's 3 atoms here, but when we're dealing with molecular geometry, we're doing it based on the central atom. So we're saying how many are connected to the central atom. Same thing with lone pairs. When we look at number of lone pairs, we're not looking at every possible lone pair on the whole molecule, just on that central atom, the ones affecting the geometry. So number of lone pairs is 0. So what do we call that geometry? Yeah, that's just linear. Only 2 groups, they're going to stretch out as much as possible. And so what's the bond angle here? And what is it? It is ideal. Yeah, so it's going to be 180 degrees and just the ideal angle. Okay? So if it were greater than or less than, we'd say greater than or less than whatever that number is. So see if you can do that for the rest of the ones on that list. You can work together as you would in the lab. And we'll hold off on the second half of that for Thursday. If you don't have the sheet out, there they are.
Joe?
Yeah.
So, just so I get this right, so when it's less than, or equal to, there's like the octahedral, right?
Mhm.
Like, or not, yeah, I guess you get like 180 and 90 degree.
Right. So you put both of them in there.
But then when you move like less than, like,
Well, with octahedral, you would only have 90.
I know, but I was
That's
like,
the closest.
you had like a 90 and
120.
120.
So you put both.
I know, but what is the less than equal to 20?
Okay, so like with a trigonal bipyramidal, like a seesaw type shape.
Yeah.
The lone pair is far enough away from the 120 ones that it's not going to affect it.
Yeah.
So the 120 ones are going to be right on ideal. But the 90 ones are going to get pushed a little bit. So you'd expect the 90 degree angles to be a little bit less than 90, but the 120 to be ideal. Yeah.
So the molecular
Right.
okay.
Yeah, if they don't bring enough electrons in for that to work, so that's everything. Pretty much everything to the left, 3A to the left, so 4I to the the other ones are all else.
Well, within the bond, I want to see if we can. So that's what it's saying.
So here this one. I'm not sure what this- Oh, the house.
Yeah, because the vice president's not factored. So if these are square, we have so this was the electron geometry is the way to draw. But it's got two lone pairs, which means the atoms are in a square plane.
Okay.
Like they're exactly this kind of shape. Like that. So that's an idea. So the one day after that, yes. But the greater than or less than thing is, if you have lone pairs, they push everything away. In that case, there's one on the top, one on the bottom, so they're not pushing away in any significant way. Yeah, they're just because they're kind of canceling each other out. If there were just one pair on one side, they would expect it to push everything else away to the other side. And the bonding will be a little bit less than
We've got about 15 minutes left. So let me know if you have any questions on these. We're not going to go through all the answers because it's a lab and you can do it, and we've got the rest of it to finish anyway. But let me know if you have questions. If you're done, you can go quiz tomorrow. First thing, yeah.
I see how you did C.
C. Yeah. So C. I think C is actually
Yeah.